Good afternoon, everyone. Thank you all for being here again and participating today in the SISSA IFPU webinar on gravity. Today we have with us Macarena Lagos. Macarena is currently a postdoctoral fellow at Columbia University. So during the last years, she has been dedicated to the study of different topics, those being origin and evolution of our universe, the nature of dark matter and dark energy, cosmic inflation, testing general relativity with gravitational wave observation. She got her PhD in physics at Imperial College London under the supervision of Professor João Magalhães. And since 2020, she has been working at Columbia Astrophysics Laboratory. Today, she will talk about interacting gravitational waves. Oh, go ahead, Macarena.
Thank you. Thank you very much for inviting me, for having me here. So I will be talking about how we can learn about cosmology from gravitational waves. In particular, how we can test the field content of the universe, meaning probing whether there are additional fields that may be interacting with gravity, maybe in a non-trivial way, that end up leaving some imprints on gravitational waves. So let me just start with a short introduction. So, we study cosmology modeled by the lambda CDM model. These are the universe constituents that we believe are present right now. And already from a theoretical point of view, there are a number of questions regarding what's the actual nature and behavior of dark matter and dark energy. Now, from an observational point of view, the lambda CDM has been overall doing very well, but now that we are reaching more and more precise observational constraints, some tensions have started to appear. And I mentioned here the famous or infamous H0 tension and the tension that exists between late time observations and observations that make assumptions about the early universe. And these kind of tensions are emphasizing even more the need for testing cosmology and actually testing whether the assumptions that we're making about the lambda CDM universe are actually correct or not. So that is going to be the goal here. And of course, we will have a number of kind of the usual electromagnetic cosmological probes coming, and new observatories coming in the next few years regarding, cosmic microwave background and galaxy surveys. So we will have a lot of more data to do this task. But here, of course, I want to focus on gravitational waves, and they can be useful in two particular ways. One is that they could provide us with independent constraints on parameters or quantities that maybe we can already constrain with the usual electromagnetic cosmological probes. That's the example of H0, the Hubble rate, and there are already some independent, although weak, constraints that come from gravitational waves alone. And on the other hand, it could also be possible that gravitational waves are more sensitive to certain effects or parameters that maybe just electromagnetic, the cosmological observations are just not that sensitive to and cannot constrain that well. So that's the idea that we have in mind for using these extra gravitational wave probes, and we already have some detections from LIGO and Virgo. Now CAGRA has joined the network, and hopefully in the future we will have detections of gravitational waves in a wide range of frequencies, from nanohertz for pulsar timing arrays to 100 or 1,000 hertz for ground-based observatories. And what that basically means is that we will be detecting gravitational waves from different kind of sources that are actually also located at different redshifts. So we will probe different depths of the cosmological evolution. So this is the idea that we have behind. And how do we use actually gravitational waves to test cosmology? Well, by studying the propagation of gravitational waves. So we're going to have in mind that they are emitted in some, dense gravity regime, and of course the emission physics will depend on that, or how gravity behaves in the strong field regime. But after that, these waves propagate on this almost empty space, and in the propagation is when we are going to test cosmology. And in this talk, I'm going to be assuming that the emission of gravitational waves is going to be the same as in GR. That I mean, that is based on the one hand on observations that so far, there aren't at least any visible measurable deviations from GR, but also because to feed these observations, modified cosmological models usually are constructed in such a way that in the dense, strong field gravity environment, all the deviations from general relativity are usually suppressed or hidden. So let's just focus then not on the emission process, but just on analyzing how waves propagate on a perfectly homogeneous anisotropic universe. So here I have, the main equation determining how gravitation waves propagate in GR or lambda CDM. So we have, our metric that is minimally coupled to, all the rest of the matter components. I actually include here, dark energy and dark matter, photons and everything. And this is the equation that tells us how they propagate. Here, HP is the actual amplitude of the gravitational waves. P is just a subscript for the two polarizations that are carried in GR. And here I'm working on spatial Fourier space. So my gravitational wave field is a function of time and the wave number K. So from here, just from this very simple equation, we can see that the 2 degrees of freedom or polarizations in general relativity propagate in the same way. They both satisfy the exact same equation. This term here that is proportional to the first time derivative of h tell us that the amplitude of gravitational waves gets kind of diluted with the expansion of the universe. There's this Hubble friction effect. And this term tells us that gravitational waves propagate at the speed of light. And now the question is, what if we change some of our assumptions about cosmology? In particular, the main motivation that has been, going around in the past, I don't know, decade or more, it has to do with testing dark energy, whether actually is an exact constant, or maybe it is something dynamical that evolves in time that maybe right now is nearly constant. So that is the idea that we will have behind. Typically, we're going to promote the cosmological constant now to allow it to be a dynamical field. And it could be anything. It could be a scalar field, and then you have what are called the scalar tensor theories, or a vector field or a tensor field. And you could also have multiple fields. That's also something that people study. And typically these kind of dark energy fields may have non-trivial interactions with the metric itself, G mu nu. So we want to probe what's the nature of this dark energy field, and also how does it interact with the metric. And we're going to do that by analyzing how it can affect the propagation of gravitational waves. And here I highlight in blue different modifications that can typically appear in the propagation equation. So the first one is this parameter alpha m. It's kind of a new friction term. So now the amplitude of gravitational waves does not decay just because of a Hubble friction, but also because of this extra term that maybe depends on time, and maybe it is a constant that will depend on, will change model by model. But this, because it affects the amplitude of gravitational waves, it can be, for example, easily constrained with observations of gravitational waves that also have an electromagnetic counterpart associated. So that, for example, already happened with the 170817, the only confirmed event with an electromagnetic counterpart. And in this paper, we put some kind of very mild constraints on this alpha m parameter just with that single event. We also show some forecast that can be done for LIGO on how well could you constrain this kind of friction modification in the future. If you had many, maybe 100 of these kind of neutron star sources that emit also electromagnetic counterparts. Now, in general, I would say that like according to our forecast, LIGO may not reach very strong constraint on this alpha m parameter compared to what a standard cosmological probes could reach. But that is not the case, for example, for LISSA. So other people have shown that LISSA could set a strong constraint on this alpha m that will be competitive and will improve the constraints that you could impose using CMB or galaxy surveys. And the other effect that I want to mention here is this parameter alpha t. We're going to call it the tensor speed excess, and it modifies the propagation speed of gravitational waves. And it could depend on time again, or a constant, or maybe it could depend on the wave number itself, which would change the dispersion relation that gravitational waves satisfy. And again, this alpha t parameter would make the propagation speed of gravitational waves deviate from the speed of light. So it can again be easily tested if you have a source that emits electromagnetic waves and also light. So then you compare arrival times. And again, just the single event 170817 actually imposed constraints that were much stronger than any cosmological constraints that could be imposed previously. And in this paper, for example, we showed how that affected a number of specific dark energy models that people typically study in the literature just because of that single event 170817. So finally, this third term here is the possibility that gravitational waves may be interacting with other tensorial degrees of freedom, other fields that here I just represent generically by this variable psi. It could be just one extra tensor field, or maybe there could be many. And this is what I'm going to be focusing on in this talk, mainly because these alpha m and alpha t effects have been studied a lot lately in the literature. Here I showed you, I mentioned you two specific papers that I was part of, but there are a number of authors that have worked on this. So I'm going to be focusing on what's the effect that interactions with other tensor fields may have. But before I move on to that, let's just summarize what to generically expect when you have a, well, I call it modified gravity, or modified, cosmological model. So there could be a modified friction that changes the gravitational wave amplitude. There could be a non-zero alpha t parameter that modifies the dispersion relation of gravitational waves. Something that I haven't emphasized yet is that the two polarizations, plus and cross, could actually propagate differently, either because maybe these modifications, alpha m, alpha t, actually depend on the polarization, like maybe they are different for plus and cross, or because plus and cross interact differently with the additional fields. And in the particular case, when we have interactions, the main kind of physical feature is that there will be an exchange of energy between gravitational waves and the additional new fields. And this is what I will be showing, what can that actually cause in a waveform of gravitational waves. So something that can typically appear when you have interactions with other fields is actually a modified dispersion relation, and I will show how that appears. But just to get some intuition on what a modified dispersion relation can cause, let's just do a simple kind of toy situation of what would happen if we didn't have interactions with additional fields, we didn't have any modified friction, but we do have a non-zero alpha t parameter that could depend on the wave number k, on time or redshift z also, so that you have a modified dispersion relation like this one, where omega is the energy of the wave. So like one of the most intuitive examples to look at for a modified dispersion relation is the example of massive gravity. What if gravity was mediated by a massive graviton instead of a massless graviton? So in that case, you're going to have a dispersion relation of this form. So it deviates from general relativity just because of this mass term here. Mg is a constant, and here A is the scale factor. So a dispersion relation like this, what would cause is that if you calculate the group velocity of waves that have the dispersion relation, then you get something like this for small masses. And well, the group velocity is, these waves do not propagate at the speed of light c, but instead they do have a modification that is actually k-dependent, meaning that this group velocity is dispersive. So different frequency modes actually will propagate at different speeds. And from this particular, a formula, we can see that low frequency modes, like a smaller k, actually do propagate slower than the speed of light, and high frequency modes, high k modes, propagate closer to the speed of light. So this will bring distortions in your waveform. So this is an example of what a gravitation wave signal detected by LIGO, detected by LIGO would look like. And here we have the strain as a function of time. And we are, again, just I remind you, assuming that the emission of the signal itself looks like general relativity. We only change how the signal propagates. And this is a simple toy example of a binary of two black holes of equal masses moving in a nearly circular orbit and merging. So in gray, I don't know if you can see it, it's pretty much on top of blue, but in gray, we show what you would see in GR, which is here right below blue. And blue is what you would see if we did have a modified dispersion relation with a mass of the order of 10 to the minus 23 electron volt, and the source was located at redshift 1. And here by eye, it's difficult to see any difference. They both look pretty much the same. But now, if we increase, say, this mass by 1 order of magnitude to 10 to the minus 22 electron volts, then we do see that, well, we get the orange line, in which we see distortions of your waveform. You clearly see something that doesn't look like the signal that you would expect in GR. And in particular, we see that the signal is getting kind of squeezed, like it is overall shorter in time in total. And that precisely happens because low frequency modes propagate slower than the speed of light and slower than high frequency modes. So in these, in spiraling binaries that are merging, typically the gravitational wave signal has this shape that we see in blue, where the first few oscillations that we see correspond to the in spiral, and these are waves dominated by low frequency modes, whereas here where the wave or the strain is peaking, that corresponds to the merger, and that signal is dominated by high frequency modes. So the fact that low frequency modes propagate slower means that the in spiral part of the signal, let's say these first few oscillations, are arriving later, after than what you would expect in GR. So that's why at arriving here, and you see the overall signal squeezing. And what if you had an even larger mass? That's green, and that is like a more extreme situation in which the in spiral part of the signal gets so lagged behind that it arrives after the merger. So you get some kind of inverted waveform, which is green, where the signal, peaks here, that's the high frequency modes, and here much later are the low frequency modes or the in spiral part. Now, clearly, we don't see anything like this with LIGO, so we should be able to do constraints on mass, right? And indeed, using the entire population of current confirmed events by LIGO, this is the constraints that the LIGO-Virgo collaboration has imposed. So the mass has to be more than 10 to the minus 23. And this is a very good constraint, actually. It is competitive because like model independent constraints imposed in the solar system for what the mass of the graviton could be are actually a little bit worse than this. So this is actually one of the best constraints for this massive model independent massive gravity scenario. But one thing that I want to emphasize, and that's actually valid for all the propagation distortions effects that I will be mentioning in this talk, the distortions, because they are caused due to propagation effects, they accumulate over time. So if we have sources that are further and further away, you would expect more visible distortions. So this is particularly useful because even if we don't see anything with LIGO, maybe if there were some, I don't know, modified gravity or some non-trivial cosmological scenario actually happening, we could see modifications with the next generation of gravitational wave detectors that will see sources at much higher redshift. And phrasing that in a different way or from a different perspective, we should be able to impose much stronger constraint on the mass of the graviton with the next generation of gravitational wave detectors because of this effect that distortions accumulate over time. Also, at least in this particular example, for lower frequencies, the group velocity is further away, deviates more from the speed of light c. So actually the distortions effects that we will see are also more noticeable and easier to measure if we are observing lower frequency gravitational waves. So LISA also would help constrain even better these kind of distortions. So, okay, in this example, I didn't have any interactions with additional fields. We just changed the dispersion relation, and here you can see what kind of weird distortions you can get. And now we're gonna get into what happens if you have interactions with additional fields, and we will find that modified dispersion relations are a common feature that you will end up seeing. So we're gonna rewrite the propagation equation of gravitational waves, but now adding one extra field. And you could add more if you wanted, but this is, for concreteness, let's just add one extra field that we call S. Again, it's some kind of tensorial degree of freedom with two polarizations P that interact with gravitational waves. And so this is kind of the operator that determines our equations of motion that rewrite in this matrix form, and some terms that would make this equation deviate from the equation of motion of GR are here highlighted in blue. You could have other terms that I haven't written down here, but these are the ones that we actually analyze. So a matrix equation of motion like this was already proposed in this paper. And what we do is actually extend and use the same kind of generic formalism to study deviations from GR, allowing for additional interactions. And we actually analyze exactly what happens to the strain and gravitational wave signals when you have interactions. And I will show you one explicit example. So, here in these three blue terms, we are allowing for this a first derivative interaction here in time and or space that have actually these generic matrices here that would mix these two fields, H and S. And we're also going to consider as an example the case of just a non-derivative interaction between these two fields through this kind of mass matrix. So the idea is that we're going to be as generic as possible. Just consider some general shape for this matrix, for these blue matrices, but this is motivated by theories that people do, like specific models and theories that people do study in the literature. For example, mass interactions, like a non-diagonal mass term here, mass matrix here, does appear when you have the metric having non-derivative interactions with additional fields. And this is what happens in massive by gravity. When you have two metrics, they interact only through a potential term, and you end up getting an equation of motion that has here a non-diagonal mass matrix. Now, another example for this friction, like when you have first time derivative mixings between these two fields, well, in order for that to appear, you do need to have extra fields that have derivative interactions with the metric. And this, for example, happens in the so-called multi-proca theory. So here, actually, fundamentally, the theory doesn't carry another tensor field, but in this case, there are multiple vector fields. So you can have three vector fields that have some internal symmetry, and therefore that as a group together, they behave as a tensor field that interacts with gravitational waves in this homogeneous anisotropic background. And finally, we also allow for this other kind of interaction that is proportional to first spatial derivatives, that we call it, the polarization or chiral interaction, that typically is going to break. It comes when you have theories that break the parity symmetry of your system, meaning that left and right polarizations will not propagate in the same way. So when you have these, then, well, the 2 degrees of freedom in GR or polarizations will have to be studied separately with their own equations of motion. And this can happen in Yang-Mills theory. Again, you have multiple vector fields with some internal symmetry that makes them behave as a tensor field at the end of the day. But these vector fields actually behave differently for left and right polarizations. So this is just to motivate some of the theories that would actually be described by an equation of motion like this if you choose a specific forms for these blue matrices. So in general, what kind of features would we expect to find for the propagation of gravitational waves when you have interactions with additional fields? Well, the main feature is that gravitational waves will exchange energy with the additional field. That's fine, I had already mentioned that. But more precisely, what we will see is an effect similar to what happens with neutrino oscillations, that basically these matrices are non-diagonal, but you could, well, not always, but there may be solutions that we call the propagating modes that actually effectively diagonalize these equations of motion, and those describe the actual 2 independent degrees of freedom. I'm going to be calling them the propagating modes. I'm going to be using that name. And the gravitational wave signal H will be a linear combination of those 2 propagating modes. They are the ones that are effectively diagonalize this equation of motion. So we have some work in progress. We hope to have out our paper in a few weeks, but the main result is that, as I was saying, we're going to write down the gravitational wave solution as a sum of 2 waves, basically of 2 solutions that correspond to the 2 propagating modes that I was just mentioning. And in order to obtain analytical solutions like this, we're going to use the WKB approach. So normally these equations of motion cannot be straightforwardly analytically solvable, either because you have this mix between the 2 equations that you maybe cannot exactly diagonalize, but also because all of these matrices and the coefficients in the equations of motion will depend on time because of the cosmological background evolution, and that also causes difficulties for writing analytical solutions. But one could use the WKB approach. So basically we assume that the Haber rate or the cosmological background evolution is much slower than the gravitational wave signal. So we could apply this to LIGO, LISA, etc. And in order to obtain a solution like this, we're going to assume, and I already mentioned this before, that at the moment of emission, only H is emitted. So there's no emission of the extra field S. However, because there is an exchange of energy between H and S, S will be generated at non-zero at the moment of detection, although we're not going to detect it directly because we're assuming that H is really what is coupled to matter and that describes the gravitational waves that is going to be detected. But because of this assumption is that we can write a solution like this. So the gravitational wave signal is going to be this reading as a function of what we would expect in GR with these extra modifications. And here I'm dropping the sub P for the polarization, but there should be a solution like this for each polarization. Maybe the polarization is propagating the same way, so all these modifications from GR due to propagation effects do not depend on polarizations and are the same for plus and cross, but you could also have, as I was saying, some parity breaking system that makes left and right polarizations propagate differently, so all these terms here may depend on the polarization. But okay, so what are these extra terms? Well, here we have our two propagating modes, the first one, the second one, and they generically have a modified dispersion relation. Each one of them may have a different dispersion relation that is different to the one in GR, the omega equals ck. Also, they may have some non-trivial amplitude that may depend on time, on the wave number k, that would also affect, make our final signal deviate from GR. And this plus sign here is telling us that we are superposing these two propagating modes, that effectively these are two waves and they will interfere with each other, basically. And I will show you an example of this interference effect and how it changes our waveform. So let's do an explicit example just to illustrate these effects. So again, I want to use massive gravity or massive bigravity because I think it's just more intuitive than other situations. So we're going to assume that this is the equation of motion. It's going to look very simple. So there is no second order derivative mixing here between the two fields, but there is only a mass or non-derivative mixing between H and S. And here, actually, this equation of motion, we are assuming that it is satisfied for, not for H and S, but for the renormalized fields, AH, where A is the scale factor, and AS. So this is just to get rid of terms like the Hubble friction that I showed you before, that we know those are always present, even in GR. So that here, in this operator, I don't have any first-time derivatives with Hubble friction. And now these mass matrix elements actually may have different time dependence, we don't know, but just for concreteness, we're going to assume that they all evolve in the same way in time, proportional to the scale factor A squared, and these are constants. Now, if this equation of motion comes actually from an action principle, then this should be symmetric, which is what we have here. So the off-diagonal terms are the same. And motivated by massive bigravity, the actual, it's called DRGT, massive gravity or massive bigravity, we're going to also impose this extra constraint on the parameters of the masses. So actually this matrix has 3 free parameters because it is symmetric. Now with this extra constraint, we have 2 free parameters that are going to, fully determine our deviations from GR. So the idea is that we use our WKB approach. So it's like a hierarchical approach where we assume that the frequency of the wave is much larger than the Hubble rate. And at first order, you're going to get a solution like this. So in this example, there's no chiral interaction or anything. So both polarizations propagate in the same way, both plus and cross. And this is the equation that expresses how they propagate. So this is the first propagating mode. This is the second one, and we superpose them to obtain the final solution. One thing that you can see here is that this first propagating mode doesn't have this exponential term with the dispersion relation, and this is because this first propagating mode has the same dispersion relation as GR. So this describes actually a wave that propagates at the speed of light. But this second propagating mode does have a modified dispersion relation, which is actually given by a massive graviton, which is the same example that I showed you before. And what this means is that this second propagating mode does not propagate at the speed of light. So here we are adding up and making interfere two modes or two-wave packets, sometimes I call them, that have different speeds. Also, we see here that this entire solution has two free parameters. I was saying that in this case, are constants in time. One is this parameter theta, which is called the mixing angle, and is representing what is the relative amplitude of the first propagating mode and the second one to the total gravitation wave signal. And this is the second parameter, mg, which is telling us how much the second eigenmode dispersion relation deviates from GR. And we can recover GR by choosing a mixing angle equal to 0. So this is 1, this vanishes, and we recover that, our signal is equal to the signal in GR. And you could also have what is called the maximal mixing angle, which is when these amplitudes are both the same, cosine is equal to sine. And both propagating modes contribute in principle equally to the total signal. So this is like a very simple analytical solution that we can write. And then here we were working, we have the signal as a function of time and k. So we can obtain the signal in real space just by Fourier transforming this. So if you do that, then what do we get? Well, here is like the different panels show what is the gravitation wave signal that you would detect if you had these massive by gravity interactions when the source is located at different redshifts. So effectively, the different panels are showing what you would expect if the wave was propagating for longer and longer. So the redshift here is increasing down. So in this case, we have fixed our parameters so that the mixing angle is maximal. As I was saying before, the two propagating modes contribute equally with the same amplitude to the total signal. And we have a mass of graviton of 10 to the minus 21 eV. So in all the panels in gray, we show what is the signal that you would detect in GR, and in blue is the actual signal that you obtain due to interactions with this extra tensor field. So in the first panel, when the signal has been propagating for a short amount of time, well, cosmologically short, then you obtain one kind of distorted signal, but it is one signal. When this happens, we say that we are in the coherence regime. But in the bottom panel, when the signal has been propagating for a long time, you do see two separate signals. And when we have something like that, we say that we are in the decoherence regime. And this happens because the total gravitation wave is a sum, is an addition of two wave packets, the two propagating modes that propagate at different speeds. So they are emitted, simultaneously, the two propagating modes. But then one is propagating at the speed of light and the other one is slower. So, as they propagate, the slower one kind of lags behind, and eventually the two signals could get completely separated. And this is what happens here in the bottom panel that we call the decoherence regime. So now let's look at these plots in more detail. So for very low redshifts, we already see, big effects with this value of the mass mg. And what we see is that there is an interference effect of the two propagating modes. They are getting mixed, and this leads to one effect, which is this overall modulation of the amplitude that you can see here. But also there are phase distortions, in the sense that like locations of peaks and troughs between the blue and the GR gray signal are not the same. So it's not just a simple, amplitude modulation. And as I was saying, this happens because the two modes are interfering with each other, which can be seen here. So here we are plotting separately the two propagating modes. The first one that we call H1, the second one H2, and the blue total signal is the sum of both. And here we can see that, well, they have a different phase. There is like a phase shift between the two modes, H1 and H2, that actually depends on the frequency. So the phase shift changes across the signal. And for example, in this region, it looks like both propagating modes are in phase, so they interfere constructively. But in other regions, like here or here, they are out of phase and interfere destructively, and that's why you get these dips in the amplitude, this kind of suppression in these regions. So I do want to emphasize again that here you don't get just an overall modulation of the amplitude, you do get phase distortions. And the reason why I want to emphasize this is because there have been some previous papers ignoring these phase distortions and just saying that there's only an amplitude change, but that is actually not the case. And phase distortions are really important because generally we can measure better, like more precisely, deviations in the phase of general relativity compared to the amplitude. So now what do we get in this if the wave has been propagating for a longer time? So this is the second panel, and we just get some kind of weird shape that has no name other than scrambling. So here, in order to understand why we get something like this, it's better to look at this panel again, where we are looking separately at the first eigenmode and the second one. So we have the first eigenmode, the orange one, is the one that propagates in the same way as GR at the speed of light, and this actually doesn't get distorted. It just has a different amplitude because each mode, the first and the second one, carries only the partial energy of the total signal. So this is orange, but then the second mode that has this modified dispersion relation of a massive graviton is getting distorted because of this dispersion relation. And you get some weird thing here in green, and then blue is the total. So then in the next panel, so if the waves have been propagating even for longer, then we are starting to see that the two wave packets get separated. And we call them echoes. So here you have the formation of two echoes. And in the last panel, we see them completely separately. The first echo and the second one. The first one, as I was saying, describes a wave packet that propagates in the same way as GR. So this blue signal would be fitted well by a general relativity waveform template, just with a different overall amplitude, which can actually, bias things like what is the distance to the source or the mass of the black holes. But so you change kind of your source parameters, but this still would fit well a general relativity waveform template. And we have the second echo. I mean, we call them echo just to have a word, but clearly they don't look the same as an echo. This second signal is completely distorted because it had a different dispersion relation, which is given by a massive graviton. And here we have this shape because the wave has already inverted, which is the effect that I showed you before for a massive graviton dispersion relation, where in spiral part of the signal, the low frequency modes kind of lag behind and arrive later and later. compared to high frequency modes that are contained here. So this is the example of massive gravity. Because of time, I cannot show you the other examples that we have been working on, which is what if you have friction mixings and this chirality or polarization dependent mixings. So, but let me just summarize in general the message of this talk. So gravitational waves allow us to probe the presence of additional fields. And I particularly focus on what happens when gravitational waves interact with additional tensor degrees of freedom. And I mentioned briefly the examples of friction mixing or mass mixing or some kind of chiral mixing. But of course, you may have, other kind of situations that we haven't described. But the thing is that we solve these equations approximately using the WKB approach. And because this approach is very generic, you can actually generalize easily this formalism to having any interacting fields instead of just two, to include possible modifications of the initial emitted waveform that is maybe not given by GR, but maybe by something else that could easily be incorporated here. And you could also study other type of interactions that we don't mention that could be easily done. And again, I emphasize that these distortions that are caused due to propagation effects accumulate over time. The longer the wave propagates, the bigger the distortions will be, which is different to modifications that may happen during emission. Those are kind of fixed, and they just propagate then exactly the same distortions to the detector. But for these propagation distortions, there is like this redshift dependence of the distortions. But because they accumulate over time, we can already expect future gravitational wave detectors to impose much more stringent constraints on all these deviations. And some of the distortions that I mentioned is that there could be interference of the two propagating modes that lead to either amplitude oscillations, like the first effect that I showed you in the top panel, massive gravity, or just overall amplitude rescalings, as the effect that I showed you in the last panel, massive gravity, where the first echo looks like a gravitational wave signal with an overall rescaling of amplitude. Now, these propagating modes typically do have modified dispersion relations that can cause all kinds of distortions, as I showed you for the case of a massive graviton dispersion relation. If the two propagating modes have different propagation speeds, then they will eventually decohere and lead to two signals, to two echoes of gravitational waves, although they may look different from each other, but you get two signals. This does not always happen. That will depend on what's the particular mixing between the gravitational waves and the additional tensor field. But in the massive by gravity case that I showed you, that does happen. And something else is that if we had some chiral or polarization dependent interaction between the two fields, then there would be one additional effect, which is that the polarization of the signal actually rotates during propagation. So if you emit a given polarization, like some linear plus polarization, then at the detector, you may measure something different. And this could be measured if we have multiple detectors. So finally, because of all these different distortions and therefore rich phenomenology that you can see when you have additional interactions, then I do believe that we should be able to already put some strong constraints on specific models like massive by gravity or these multi-proca theories that I was mentioning. For massive by gravity, some people have looked at some of these effects and trying to put constraints, but as I was saying before, people neglected the fact that you have phase distortions, that the signal does not look simply like a modulation of the amplitude, and therefore I would say that those constraints have to be revisited. But this is all. Thank you very much.
Thank you so much, Maca. Very nice talk. So time for questions. So you can use the button raise hand or unmute yourself. So go ahead.
Maybe Miguel, I can ask a question. Hi. Yeah. So you mentioned propagation effects and these distortions that you can use to test. I mean, the dispersion relation. Essentially, there is also. Well, I have two questions. One is that I mean, you can also, for instance, with LIGO with the 170817. Because you have an electromagnetic counterpart, you can measure actually the coincidence between the electromagnetic and gravitational signal, and that can also be used to constrain the mass of the graviton, I imagine, because a different propagation velocity will be constrained by this difference between speed of gravity and speed of light. So how does that play a role in the constraint that you showed from the LBC data? And do you expect that it will play a role in the future with LISA?
Yes, I didn't mention it because that just comparing the time delays doesn't give you very strong constraints on the mass of the graviton compared to the phase distortions themselves.
That's simply, if I understand well, because 170817 is very close. So it's like 50, what is it, 50 megaparsec. Whereas for LISA, we'll likely have electromagnetic counterparts to supermassive black holes. And then the constraints will be, I think, as strong or may be as strong as the distortion effects, isn't it?
Yes. Okay. I don't know.
I don't know either. I mean,
I haven't seen like the actual numerical comparison of both. I mean, just because, you know, as I was saying, like the phase evolution is measured. Yeah, I mean, I guess it will depend on, you know, what are the, you know, astrophysical uncertainties on the, I guess, the electromagnetic counterpart, things like that.
But yeah, I have a question about the phase as well, because you show these modulations in the frequency and phase distortions. But have you done, I mean, an assessment of really how much you can tell those differences from the GR waveforms? Because just by plotting them, it's not obvious that you can see the difference, because there could be degeneracies, for instance, with the spins. So if you have precession spins, you'll have similar modulations, right? So you really need to do a Bayesian experiment or at least a Fisher matrix to see if the effects are detectable or not, right?
Yes, I completely agree. And I mean, we haven't done it. That's part of doing actual tests on, you know, specific theories. But yeah, I mean, I agree.
You know, just because I think the degeneracies with spins in particular could be important. I mean, I don't have a.
Yes.
Well, it could depend on the signal-to-noise ratio of the system to some extent.
Yes. Yeah, I do agree. I mean, I do think that there will be like some hints as to, well, this confusion, whether you could actually confuse them or not. Like maybe you're gonna find like some light event that has this modulation, which is normally something that, like, from astrophysical populations you wouldn't necessarily expect. Like the spinning black holes are the ones that are heavier, like maybe second generation.
It's not necessarily true. It's actually the other way around. If you look at X-ray data for supermassive black holes, the highest spins are at the lowest masses. So we really don't have a clue what would be the spin distribution of the population. But I agree, yeah, there could be other hints.
Yeah, I mean, I was thinking of like solar masses, like
yeah, no, but LISA yeah, I thought you were focusing. Yeah, I was thinking about LISA. You're right.
Of LISA, okay, yeah. Yes, I agree that that's certainly something that has to be done in terms of when you are comparing whether this will be different to GR or not. You don't compare it just with a non-spinning black hole. And yes.
Well, thanks. I guess there were more comments than questions, but thanks anyway.
Thanks, Enrico. So, Sebastian, go ahead.
Hi, hello. Also, thanks again for the nice talk. I have a question regarding this effect, do you think it's interesting to stack different gravitational wave events to get, I mean, in the future to get better constraints on that, or is that difficult?
You mean for different sources?
Yes, for different binary mergers that we have seen, if it's possible to combine the events to yeah, have more stringent bounds on these effects, or is it not possible to stack them?
Well, it depends. Like sometimes you can stack them. That's, for example, what the LIGO-Virgo collaboration has done. For the case in which you have like a single dispersion relation determining your entire gravitational wave, like a single massive graviton, which is the first example that I showed before talking to interactions. You can stack them. I mean, you just have to, fit for the given redshift and luminosity distance that you obtain, fit this modified dispersion relation to all of the events that you can do. Now for this interaction situations that are a little bit, I mean, if you impose a waveform that actually does take into consideration the addition of the two modes, the fact that they will have a different dispersion relation, and therefore for higher redshifts they may decohere, they propagate at different speeds, then you can stack them like the way LIGO people did it.
Okay, thanks.
Yeah. So the constraint that I mentioned for the massive graviton was using the entire population.
Okay, more questions? We are just in time.
Yeah, maybe I can ask a quick one. Oh, hi, Macarena. I was wondering in this new effect that you were showing about the distortion of phase and so on. But if you consider, let's say, a value of in bigravity, the value of the mass that is, let's say, cosmologically relevant for dark energy and late time, will you still see something, or there is no hope that for such small mass you will see some effect?
Yeah, I mean, I think that there is this thing about what's the relevant range of the mass, because if you consider the particular DRGT massive bigravity model, then the constraints on the mass from like solar system observations are very strong, and I would guess that you would not see anything for here with gravitational waves for those kind of masses, which is like, I don't know, 10 to the minus 33 EB or something like that. But people also consider these kind of unmodeled massive gravity models. And those have these weaker constraints, which is 10 to the minus 23. That's what I was mentioning previously. That is the constraint obtained by LIGO that I said it was competitive with solar system constraint. That was for like the unmodeled, massive gravity scenarios. And for those values, yeah, we should definitely see things here.
Okay, thanks.
So we are on time. Thanks again, Macarena. Very nice talk. So see you next week, and thanks again, Maca. So
thank you.
bye bye.